September. I have September stuck in my mind for some reason. I wonder why. Welcome to the July meeting of the Madison Astronomical Society. If I could have everyone's attention. It's great to see everyone here. We are passing an attendance sheet around. If you are a guest or if you are a member, please sign it. Also, I can't believe I'm remembering to say this for once. If you have phones or such like that, you might want to put them on mute so they don't interrupt the presentation. We have a great presentation tonight. I'm Lawrence Moore. I'm the president of the society, and we have some fun things to discuss. First of all, we're getting started with the announcements a little earlier because we have a little bit more to talk about. I would first like to bring to everyone's attention that we are considering having Madison Astronomical Society like it was when the Astronomical League first got going, having Madison Astronomical Society be an affiliated organization with the Astronomical League. Since about the early 90s, we ceased being an affiliated organization due to certain historical issues that are long gone. And it's come to our attention that there might be some really easy ways without too much burden on our society to make such a thing happen. And the main idea is, you know, there are people here who would like to be members of the Astronomical League, and it would be, there's an opportunity to, you know, make it easier for everyone that are members of our society to be able to do that. Jack, would you like to fill us in about that? I'll hand you the mic here.
Does that work? Yes? I'm Jack Fitzmyer. I'm on the board of MAS and happy to be serving. Several of our members noticed this summer that there was a program up near Green Bay, a convention held by the regional association of the Astronomical League, and asked the question, hey, can we go to that as members of MAS? Actually, the answer is yes, because it's a public event. But then that kind of spun off a conversation about what's the relationship between MAS and the Astronomical League. So if you bear with me, I'll do a little bit of background about the AL, as I call it. And the board would like to, I'm speaking on behalf of the board, we'd like to open it up for questions, comments, conversation. We have not taken action. There's not a motion on the table. We are exploring this and would be happy for any thoughts that you may have about it or questions. So that's where we are in this. So give me a little bit. I was trained as an historian, so you forgive me if I start there. Around the end of the 19th century, early 20th century, there was a gigantic explosion of interest in professional societies and learned societies. And the two that most affected us, astronomers, were the Astronomical Society of the Pacific, which is kind of an international organization, which happened in 1889 and was followed about a decade later by what is still known as the AAS, which met here, I think, last year, the American Astronomical Society. This kind of proliferation of societies just didn't end with sciences. It took off terrifically in the humanities and the social sciences as well. So the American Philosophical Association, the American Sociological Association, the outfit I worked for, the American Academy of Religion, all from 1900 to about 1915 were born, and there are scads of them now. An interesting thing happened just before and after World War II, and that is that particularly in the astronomy community, these organizations, by the way, I should say, were scholarly in nature. So it tended to be college faculty member, university faculty member, lab people in the sciences. And the amateur astronomy community said, what about us? You know, I'm interested in science, I have a telescope, I go in my backyard. There's no light pollution back then. And I look up and I see stuff. And what about me? Can someone kind of serve my needs? Well, it turns out that MAS was instrumental in this movement, and I call it a social movement, really, of amateur astronomy. The lead dog in this thing was the Milwaukee Club. And in about 1935, they formed an outfit with 12 local clubs that was called the American Association of Amateur Astronomical Association, American Astronomical Association. And it went on for a couple of years, and the war happened and so forth. And several of our people at MAS were involved in this. And it turned out that after the war, this thing morphed into a thing, a national thing. It was Midwest then, called the Astronomical League. And at the start, in 1948, it was 30 clubs. So it was a league of astronomy clubs and about 1,500 members. We were a charter member, MAS was. And our leaders were very active in the Astronomical League. So not only did our people participate in the leadership, but there's national conferences and regional conferences. And we held 5 over the years, several regional conferences, several national conferences. The last one was in 1996, and something went amiss. I've read part of the record, and a lot of people were extraordinarily unhappy with the way this meeting came about. So in what I think is kind of an unusual move, MAS decided to break ties with the Astronomical League. And we were no more a part. So we'd been a charter member. After 96, we were no longer a part. Maybe it was 93. In any case, it's ancient history. In 2001, someone said, hey, what about, just like they had this summer, hey, what about the Astronomical League? Should we rejoin? And there was quite a debate in the club about it. And the answer was no. And the leading arguments for not rejoining were 3. One was that it was too expensive. Membership was too expensive. The second was that at that time, those folks didn't think there was enough bang for the buck for the club. We didn't get enough back for our investment. And the third was kind of, I thought, a dig. This was actually in the newsletter. The dig was that the Astronomical League has lost its way. It really doesn't have much purpose, which I think is rather churlish to say of another organization, but it was said. And interesting, it was said that this is because all they do are these meetings. That's all they do. So it's kind of come down to me to sort of do a bit of research on this, and I just want to revisit very briefly those 3 questions and bring it up to date. A lot has happened since 2001. The first question is membership in the Astronomical League expensive? And I want to make the case that the answer to that is no. It's not particularly expensive. The AAL has gotten very cagey. Typically, for an organization of organizations, what they would do is say, okay, how many members do you have? We happen to have about 132 at present. They'd say, well, give us, in this case, $6 a member every year, and all your members can be a part of the Astronomical League. So if we did that, we could do that. They would like very much for us to rejoin. It'd cost something less than $1,000 a year. That's not small potatoes for us, but that's not an enormous amount. But the AAL has gotten clever. And that what I just described is called a full membership. They have what they call a partial membership, a full club membership. No, FOOL, it's not. The Motley Fool. There's this partial membership, which I didn't know about till recently. It's clever. They say, oh, you want to join, but you're worried about the money? Well, here's the deal. If you can get people in your club to raise their hand to say, I'd like to be a member of the Astronomical League as well as MAS or whatever the other society is, just give us a list of those persons. And instead of $6, give us $9 a head. So a few people at MAS, if they'd like to be involved in the Astronomical League, could do so. And we would be a member association, but not all of us would participate and have membership. Not bad. If we did it that way and 20 people wanted to join, it'd cost the club a couple $100. I'm an at-large member, and it cost me $40 a year to be a member. I've been a member for a long time, and I've been very active. So I don't think it's expensive. I don't think it's burdensome. Is there bang for the buck? I think there are quite a few benefits. Some you might think modest. I asked the fellows to pass out a copy of this, which is the quarterly magazine of the Astronomical League. There's several issues, and there are probably stacks more if you'd like to pick up others. The other is their brochure about who they are and what they do. The benefits, I think, are, for that amount of money, are considerable. You get the Reflector on a quarterly basis. There's a regional newsletter because we'd be part of a region here in the upper Midwest. There are discounts on publications that you can get through their website. There's all kind of swag. There's award programs. There's discounted club liability insurance, so they do things for clubs. They try to encourage good best practices in clubs. There's a lot of materials for outreach, which is something we do, I think, occasionally at least, but there are a lot of things you can use with a bunch of newbies, and they produce those materials and make them available. There are these annual conventions. I'm actually going to go to my first one this next week in Kansas City, a national one, and then each year there's a regional one. And then there are the observing programs. So in the last few years, there's been kind of an explosion again of AL observing programs. And what this means is that they sponsor a peer-reviewed program. So let's say you became interested in double stars. You could do an AL program in double stars. And what that would mean is you would get a list of double stars, typically about 100 targets, and you would have to find those targets in the night sky, describe them, sometimes sketch them, say where you were, what time it was when you viewed it, put together a log, submit the log to a peer reviewer, and if they approved it, you'd get an award. And the award typically is a little certificate and a lapel pin. I think I wouldn't be who I am in astronomy if it weren't for the several dozen of these that I've completed over the years. I think they're fantastic. And my wife thinks it's just because I'm anal retentive. I like filling out a log and making sure I have the time right and so forth. Maybe it is, but it appeals to me, and I think it's a great way to learn the night sky and your instruments. There's all kinds of programs, from radio telescope to imaging to visual to binocular to you name it. So I think that would be something that would appeal to our members and also would allow us to use YRS more effectively. And to press, we've put all this money into the new pads. We'd like to press to get as many folks out there as we can. One really cool way to do it is to do these observing programs. So I do think there are benefits. Are there costs to us? Yes. If you're an affiliate, you have to have your president or the president's proxy on the council at the regional group. They typically have an officer they name in the local group that serves as the liaison. I did that for the Atlanta Club for years. It's really not that big a deal. Probably the biggest administrative load would be on our membership because we have to either send our rolls if we did the full membership, or if people were interested, send a list. I made a recommendation, it's mine alone, to the board and said, I think we should pursue this. That has no force. The board hasn't had a formal conversation about this yet. I did it for these reasons. Number one, I think we always have to look to add benefits to membership. It's incumbent on me, I feel, as a board member, to find reasons for you to rejoin or to join in the first place. Secondly, Dave may want to speak to this. We know clubs have been kind of revitalized by this. Milwaukee's a really good example. They use the AL in terrific ways. Dave wrote about that to the board. I think there's some collegiality involved. We hosted the Lake County group a month or so ago. It was a fantastic event. We could do that all the time. There's clubs all around that we might do that with. As I say, I think it might drive people to YRS. And finally, as an historian, I'd like to claim a bit of that heritage. MAS really was at the heart of a movement in amateur astronomy. And for me, I think it would be really cool to sort of reconnect with that. So again, the floor is open for comments or other things people want to say. Questions? Sure.
Yeah, Jack, one of the, we've talked about it. Can you guys speak into the microphone? Okay, sorry. There's just a couple of things that we should also be aware of in here too. And Jack, you admitted that if we were part of the society, especially as a full membership, we would get a considerable amount of pressure to host our own convention at some point in the future. That personally scares me a little bit, because when I look at how hard it is sometimes to get our membership out to Moon over Minot or things like that, a convention is a huge deal. There's a lot of work involved in that, and I frankly don't know if we have the bandwidth to do something like that, and I think that would require some pushback.
Not to mention the cost and potential cost, liability, and cash flow issues.
Yeah, and their conventions sometimes make money, and my understanding is that if it does make money, they will get 75 to 85% of the profits, and we get the other 15 to 25% of the profits. And the same thing, if it loses money, they take on some of that liability too.
Yeah, I don't know the details, but I think were we to do this, we should expect to kind of be lobbied at some point. This is for a regional meeting.
Like the one we had in the Green Bay area, I forget.
Yes, the pair, yeah.
The pair
Yeah. We're capital. We have access to terrific speakers. Madison's a great city, and they have a devil of a time finding hosts. So I have said to the board, we'll probably get lobbied. And I said this to the regional guy and made it clear that I wanted to make sure that he knew that we wanted to be able to say, if we needed to. A few years back in Moline, there were about 135, and this last time was quite disappointing to the region. There were only 58 up near Green Bay this last spring. Attendees.
And they would look upon Madison as being, not just because of a metropolitan center, but also for being a university town, as being a real plum to have a convention. So we will receive a good bit of pressure to do that. One of the things we also talked about is under a full membership, and I think I heard from Jürgen that that would be about 10% of our budget that we get annually. So it's a considerable chunk if we do a full membership, but at the same time, if we did a partial membership, then it's like you were asking those people that want to participate, and like in your situation, Jack, you're actually saving about $31 a year as part of that membership. If we asked you to go ahead and pay your $9, the only other charge to the club at that point is $10 for the general club membership to allow for that partial membership. And I don't think anybody would kick about the club putting in $10 so everyone else can put in their $9.
And we haven't. There's no proposal on the table to say we pass it on to you as a member or no. My Atlanta club, nothing was passed on.
And that's saying, say if someone wanted to be a member of the AL and indicated on their membership form, I want to be a member on the AL, would there be a small pass-through cost, for that option?
And it would put a little bit more burden on our treasurer here in terms of trying to keep track of that and then sending those dues in. And we also have to figure that out because their membership year is different than our membership year, and we'd have to reconcile those figures too. So I'll let you talk to that.
Yeah, I'm the money guy, so I tend to worry about things like that. And since this would be a kind of a double whammy, because we're looking at the Astronomical League, and next year also the new dues kick in. And we're really uncertain about how many people will drop out because the prices have gone up for some things. So I tend to be a little bit more conservative. I think as the money person I should be. So I'm a little bit concerned. And if I had to vote on this right now, I would tell you that probably pass through the cost of the individual membership to the members. You'd have to pay it. will pay the $10.
Just the individual members.
Just the individual members, right. Right.
For that associate membership.
Yeah, for the associate membership. And we would handle the paperwork. But the other part of this is the alignment of the years. Because as of October 1st, we have no members. You become a member again when you renew, okay? So, you know, there are administrative
And their year starts.
crap here
And they
that would
roll
have
in
to be,
July.
yeah, that we would have to worry about. But that's something that can be solved, but again, thank you for saying it would make my life a little bit more difficult, but that's not a real problem.
That's my only purpose in life.
Yeah, I would
Thank
just
you,
like-
I appreciate
I'd
that.
just like to point out that it is 31 minutes after the hour right now, so.
One more question.
This is Mike Mack. I'd like to express my strong support for this proposal. So I came from a different city, different club. The one you mentioned, Moline, which was really Quad Cities. And we hosted the NACRO that year, and it was not a financial burden to the members. It was very easy to find sponsors for the event. And so that's how we funded it. And I think we could do something very similar here. This would be a huge draw because what you guys have that almost no other club has is you have access to fantastic speakers. The quality of what you would put on here would dominate anything that any other clubs do, I think. And I think you could fund this easily with sponsors. And to me, you know, this was one of the original founding members of this. By the way, so was the Quad Cities. I mean, to me, it just makes sense. We should get over this 30-year problem that happened. Yeah. No one is in the club now that when that happened, and I think it makes a lot of sense. So,
What was your name again?
Mike Mack.
Mike Mack, I just.
Yeah.
wanna-
No, Kevin's right about one thing. You do need somebody who is good at organizing meetings to be willing to take on the task. And that we had somebody there who that's kind of what he did when he worked, and he was happy to do it. So it's work, no question, but I think the money part is more easily solved than you think.
And I would just repeat, there's no obligation to host one of these. That's an important point. I think
Yeah.
it's time, we're running out of time.
Yeah, we're pretty much on time, so just a couple more minutes.
Yeah, I understand. I have seen this in action at Milwaukee, and Milwaukee is using it very successfully. They have several students who are members as well as family, and students and family really love the programs that the AL offers. So the board and other members here have been working to actively expand what we can offer different membership, and this is something that would work very well for that, and I've seen how successful it has been there. They also have one member who's a member of AL as well, who is a representative, and he or she sends out email when the time comes around July, seeing which members want to join, and he just collects the $9 due per year from those members, gives it to the treasurer, who then sends that in. So it works very smoothly for them. If we ever run in a situation where the league is pushing us for something to do, us to do something that we're not able to or don't want to, and we can't resolve it, we can always drop again. In my mind, there's very little downside or risk to joining.
Yes, as an associate organization. Well, thanks, everyone. I'm sorry we're out of time, but it sounds like a great idea, and I'm very interested in it. All right, John, would you like to introduce tonight's guest speaker?
Hi, everybody. I'm happy to introduce tonight Bob Benjamin as our speaker. Bob has been a speaker several times before, and always in giving his update on modeling the structure of the Milky Way, basically says stand by for updates because it's a quickly evolving field. I'll point out that it's not often that we have a speaker who expresses uncertainty about his own status in employment or otherwise. Bob will address that as part of his talk tonight. So please welcome Bob Benjamin, Whitewater and Madison Professor of Astronomy.
Okay. Thank you very much. So first of all, Yeah, just to not make you wonder, I've been a professor at the University of Wisconsin-Whitewater since 2003. Actually, as of this August, I'll be retiring, unfortunately early. My mom has gone through a really dreadful summer last summer and is in need of, she was either a nursing home or home care. So I've decided to basically, my mom now lives in my building downstairs, and so I'm going to be a caregiver who has a study set up in his mother's apartment to do research. And so I actually think this might end up being a net plus for research, and rather than all my students in the department of ornery professors, I just have my mom to worry about, and then worry about my research as well. But we'll see. That time will tell on that. But what I'd like to do is fill you in with updates. Now, I believe, although it's been a while since I've addressed the Madison Astronomical Society, I might have done a UW Space Place talk where I will have said some of the things that overlap. But for those of you who heard me speak before, if it sounds familiar, it's going to take a hard right turn in the middle of the talk and go in a very weird direction. Okay, so if you've heard this before, enjoy it again. But it is going to be different. So we're going to start off with this picture of the Milky Way. This is actually an optical mosaic by Axel Mellinger, who's a professor at Central Michigan University. What I love about this picture is the red part is H alpha, so you can see gas that's being lit up by star formation. Mostly what you're seeing is points of stars, and then a lot of dust, right? I mean, that's sort of what makes the Milky Way, the plane of the Milky Way, sort of interesting, but also annoying, because as an astronomer, that dust is blocking our view of the stars further into the center of the galaxy. But this is the kind of view you might have had in, for instance, the 1920s, and that's where I'm going to start the story. And I'm going to start the way astronomy story typically starts, with a love story. And it's the love story of Priscilla and Bart Bach. Priscilla was actually grew up in Boston, got her bachelor's degree in Boston University, and then went off to UC Berkeley to get her PhD. She got a PhD in astronomy at UC Berkeley, working with William Campbell, who later became the president of the University of California, Berkeley. And then she came back to the East Coast and got a job as a professor at Smith College. Now, although she was teaching at Smith College, she was also doing a lot of research in Harvard with Harlow Shapley. If you know the history of astronomy, Harlow Shapley is known for being the first person who figured out the size of our Milky Way galaxy, the fact that it was roughly 20 to 30,000 light years to the center of our own Milky Way galaxy. And so she was engaged in a lot of research. And in 1928, she went to the International Astronomical Union meeting held in Leiden that year. The International Astronomical Union is the international group of astronomers. And actually, the IAU meeting for this is actually this year in South Africa in a couple weeks. So, at any rate, so Priscilla Fairchild at the time went to Leiden. She was met at the railroad station by a 22-year-old graduate student, so a student 10 years younger than her, and he was assigned to be her sort of guide to the city to help her get situated and get to the meeting and everything like that. And so they began to talk. He sort of guided her around the city, and at the end of that week, he proposed to marriage. So the 22-year-old grad student proposing marriage to the 32-year-old professor. She said maybe not quite so fast. They continued to correspond for the year, but then Bart Bach got himself transferred. He was working on his degree at Groningen University in the Netherlands with Van Rijn, but he got himself transferred to Harvard on a fellowship so he could work with Harlow Shapley. And I think within a few weeks of arriving in the United States, he and Priscilla were married. And they together became sort of the Milky Way couple. So they were known for their research on the Milky Way. At the time in the 1920s, a lot of that research focused on the distribution of stars in space and also the distribution of dust. So you look at these bands of dust and you say, well, they're blocking out stars. We sort of knew that by the late 20s. And so where are those dust clouds? If you know where the stars are, maybe you can figure out where the dust is. And what I'll tell you now is that I can tell you now where all of those dust clouds are. And I can tell you with a 3D visualization that we can fly through. And we are now at the point in astronomy where we are routinely doing things in the last few years that actually I never even thought were possible. And so we're going to get to that later. But when I look at this picture now, I see all the depth of it, okay? In particular, I guess I need to point to this in the pointer, a few points, you may notice this dark band of dust that's sometimes called the Great Rift, or it's sometimes broken up into the Aquila Rift and the constellation Aquila over here, and then by the time you get over here to Cygnus. But that band, particularly this part of dust, is actually a giant ring of dust in the sky, edge on, okay? And it's about 300 light years across. And actually, I have my laptop cover is actually a map of the Milky Way, showing the distribution of dust. And you probably can't see it, but there's a nice ring right here that is that thing seen in the sky. But we can actually now map it from what it would look like above. So going back to the box, they actually wrote a series of books. Actually, it was the same title, The Milky Way. Their first edition was in 1941. The final edition was in 1983. The fifth edition of that book was in 1983. That last one Bart Bach wrote after Priscilla Fairchild had passed away. And it's sort of sad to read the foreword. But if you actually look at that series of 5 books written over a 40-year time span, you can see our understanding of the Milky Way evolve. And but back in 1937, Bart Bach, in a different book, not a non-popular thing, it was actually a treatise for astronomers. So many of us at Harvard Observatory are engaged in investigations dealing with galactic structure. And while we may disagree on many different points among ourselves, it's only natural that we agree pretty well on what are the outstanding problems with galactic structure. I threw this up for some of my Harvard colleagues, who are some of the people responsible for making these dust maps, because it's ever the same, right? We may not agree on the things, but we do agree on the problems. And so at the end of this book on the distribution of stars in space, which also talked about the distribution of dust in space, Bart Bach ended his book by saying the observer in the tropics should not find it difficult to accept as a working model. By the way, he mentions the tropics because if you go further south into the tropics, like sort of the equator, then this galactic center is directly overhead, and you can see the whole sort of swath of the Milky Way above you, with the center of the Milky Way almost above. But you could accept as a working model for a Milky Way system one with a distant center in Sagittarius, in which a spiral arm passes from Carina, which is the regions of star formation you see on the right there, through the sun towards Cygnus. So essentially, even back in 1937, he was trying to sort of put together this picture of the sky into a 3D picture. And he said Sagittarius would be in the direction of the center, but then you would link the Carina arm and the Cygnus structure over here on the left, and that would be 2 anchor points of a spiral arm passing through the Milky Way. Now, there was no hard evidence for that, and I'll talk to you a little bit about how this picture came together and how it's falling apart, okay? And so we're going to start with the putting together part. So the assembly of the models of spiral structure for Milky Way. Then we'll talk about the testing of the models, and now fixing the models is where we are today. So how many of you have seen this picture? A few of you have had the opportunity to see this. This is a picture taken in December 1st, 1951. I found this online. I bought the digital rights to it, paying more money than I care to admit, from Getty Images. But it was a picture from the personal collection of Gerard Kuiper, you may have heard of the Kuiper belt of objects in the outer part of our solar system. He was actually at Yerkes Observatory. And it was taken on December 1st of 51. From left to right is Subrahmanyan Chandrasekhar, known for the Chandrasekhar mass and the maximum mass of a white dwarf before it collapses. Bill Morgan, who I'll tell you a little bit more about in a second, Gerard Kuiper. Ben Stromgren, who was a Dane who came over, who studied hot stars and how they heat up gas around them, and Jan Oort. Now, the people shown here on the steps of Yerkes Observatory here in Wisconsin on December 1st, 1951, the one person who does not belong is Jan Oort. He was visiting. So he was visiting Yerkes Observatory. He was there to talk with Bill Morgan about questions of galactic structure. And the reason this is such a pivotal moment is because at this moment, Bill Morgan had actually collected the evidence, the first generally accepted evidence for spiral structure in our Milky Way. I mean, we know we see stars, but it was unclear how to create that 3D picture of what you might see if you were to look from above. And Bill Morgan had the very first start on that ready to go on December 1st, 1951. He presented it later that month at the AAS meeting, American Astronomical Society meeting in Cleveland. He actually got a standing ovation. It was sort of something that we knew we needed to find, and he was the first person to find believable evidence for it. I actually want to say another thing about this picture, because we're going to come back to this at the end. As I learn more about the history of astronomy, I have a greater appreciation not just of who's in this picture, but who's not. Because at this same moment when this picture was taken, there were two very famous, now famous astronomers who were inside, presumably, who are not in this picture. And one of them was Margaret Burbage, who was well known for her work on understanding the nucleosynthesis of stars and also the formation of elements in the Big Bang. So she was a major player, and she was a postdoc working at Yerkes Observatory when this picture was taken. The other person is Nancy Grace Roman. Some of you may have heard that NASA is building currently a new telescope called the Nancy Grace Roman Space Telescope. You can sort of think of it as like the Hubble Space Telescope, but covering huge areas of the sky all at once rather than tiny little patches of sky. So it'll be an amazing telescope for creating surveys of the sky, just many, basically, I think it's like 0.2 square degrees at a shot. So Nancy Grace Roman was also, actually, she was a professor at this point. She had gotten her PhD at Yerkes. She'd stayed on to work with Bill Morgan. She'd stayed long enough that the administration says, you can't keep her as an assistant. You've got to promote her. So she became a professor, although they paid her like, peanuts. And actually, it was criminal how underpaid she was. But she was here in the building too. So I actually, like I said, as I learned more about the history, I'm more like, wait, why weren't they out here? Okay, and I'll come back to Nancy Grace Roman near the end of the talk. So the discovery of spiral structure, as I mentioned, was presented at the AAS meeting, American Astronomical Society meeting in 1951. It was a physical board that basically Bill Morgan pounded a bunch of nails into a physical board. Each one of these things is a nail, and then he put a little ball on top to indicate a grouping of hot stars. And what he said was there's this band of hot stars. This dark thing is actually his estimated distance to a dust cloud. The sun would be right in the center here, and he found that there was this nice band that he interpreted as a spiral arm. This particular visualization was never published as a paper, but by 1953, in combination with Al Whitford and Art Code, who were here in Wisconsin, UW-Madison at Washburn Observatory, they published the first sort of generally accepted map of spiral structure in the Milky Way. Now, just to help you understand what you're seeing here, in this picture, the sun is here. The galactic center is oriented to the right. This is a box of about plus or minus 9 plus or minus, I always do it in parsecs, about 9,000 light years, so plus or minus 9,000 light years. And each of these points indicates a grouping of hot stars. And the key thing to notice here is you see sort of three bands, this band, and this band. And so a band just outside the sun's orbit, the sun is moving this way, and then there's a band here and a band here. This grouping was eventually called the Perseus arm of the spiral galaxy. This grouping was called the Orion arm, the one just outside the sun's orbit. And this one that's further into the center of the galaxy was called the Sagittarius arm, and eventually extended to something called the Sagittarius-Carina arm. Now, what I'm going to do now is I'm going to jump ahead almost, 70 years. Because one of the questions I always had about this is like, although Bill Morgan created this map, because of the dust, we weren't able to get much further than what he did back in the 1950s for many decades. I mean, a little bit further. But now, thanks to a European Space Agency satellite called Gaia, we have parallaxes, that is basically very, very, very precise distances of stars rather than the ways that Bill Morgan estimated the stars, which was something called assuming that a star of a certain luminosity class would be a certain brightness. And so using now these parallax-based methods, which has been revolutionizing everything in galactic astronomy, we can redo this picture, and I'll now fade it to, I actually will take all the stars that Bill Morgan analyzed back in 1953, keep the same groupings, but plot up the new distances using very, very precise measurements of the distance. And you can see that they're still there, that you've still got the three bands. So I'm using the exact same 200 and something stars that Bill Morgan used, but just updating the distances to make them modern distances with Gaia parallaxes. And the red and the blue are estimates of lots and lots of other young stars. And what you can see, where the red regions are regions where we think we have a lot of young stars, and then the blue ones are not so many. And so that band of young stars, presumably luminous stars, those three bands passing through the neighborhood around the sun exist today, okay? So Bill Morgan had it right, and which is something that I like to remind people because this happened here in Wisconsin. And so now the reason I would like to do this is because, of course, what happened is because of the limitations of how far you could see through the galaxy, just looking at these stars because of the dust, a lot of the excitement in mapping out the structure of the galaxy moved on to radio telescopes. And with a radio telescope, radio waves penetrate through all the dust, and if you can detect gas clouds emitting a wavelength of 21 centimeters and convert the velocity or the Doppler shift of that gas cloud to a distance, making assumptions about how the gas rotates, you can reconstruct from the radio data a face-on map of the Milky Way. I'm not going to say a lot about this. This actually gets quite technical, but the main point is that if you assume that all the gas in the Milky Way rotates in nice circular orbits, then by measuring the Doppler shift, one can estimate the distance of the gas. And so this began the gold rush of spiral structure, because what people did is they started looking at these radio maps. They started looking at the radio data. They started seeing groupings and patterns. In fact, let me just go back to this diagram. This is showing as a function, the vertical axis is velocity, the horizontal axis is what direction you're looking along the plane of the galaxy. And then the grayscale just says how intense is the emission or not. And you can see when you look at this picture that there are some bands, right? For instance, there's a band right here, and there's maybe a band right here. And these bands were identified with spiral arms. And so people started to look in this kind of data to identify spiral arms as seen in gas. And so there's a whole list starting in the 1950s of people making discovery after discovery after discovery after discovery, using these radio telescopes, finding these coherent structures of gas across the galaxy and naming them as arms. So you had the Sagittarius arm in 1954 found in H1, then the Scutum arm. And you know, these names may mean nothing to you, but I'll show them on a face-on map in a little bit. The Sagittarius arm, the Carina arm. One of the things that is fascinating to me is that all these arms that we talked about for instance, when I showed up in graduate school, they actually all date back to the 50s. But people had actually forgotten by that point where they all came from. So they all really were on the map by that point. And all this work led to a sort of famous picture, a famous sort of face-on picture of the galaxy, where the sun is sort of at the middle of that wedge. The center of the galaxy is to the right. The reason there's a big wedge taken out of the galaxy is because in the direction of the center of the galaxy and the direction of the anti-center, gas is moving parallel to us, so there's no Doppler shift. There's no tendency for the gas to move towards us or away from us. So we can't use this technique to map things sort of towards the center of the galaxy. It creates sort of a zone of exclusion. But to the left and to the right, we can make this map. And this is a very famous map. It was actually in many museums of the time. And it's beautiful and suggestive and wrong. And there were some serious problems with this map. And I'm not going to go into the details, but essentially, the history of galactic structure is a history of false starts and failed dreams. And one of the problems with these kinds of maps is that, first of all, you are assuming circular rotation, which we know is not happening. Second of all, if you have variations from circular rotation, what you think look like these arms can actually just be a mismatch between the rotation you expected and the rotation you actually have. And so it became a serious problem. But there were other problems. One is, remember I told you there's that wedge where you can't map. That means if you want to map a coherent spiral arm across the galaxy, you have to choose, I see something in the left of this galactic center, I see something to the right of galactic center. How do I map those structures together, or the structures I think I do see? And so people argued about this, and how you decided to connect things through galactic center made a very different picture of how you would map the spiral structure. And then there's the other issue, the rubber sheet problem. there was a astronomer at UC Berkeley who said, he thought, let's forget about trying to make this face-on picture. Let's just plot it up as the data we can take, which is we can measure the direction, we can measure the Doppler shift, and just that's our product, that's our map. And he said, and then we'll just stretch it. And people can stretch it different ways, but it turns out even that is problematic. And so by this point, the Bachs, who are sort of keeping tabs on all of this, sort of decided to abandon ship. Actually, I found this in a biography of Bart Bach. Once, as they were both sitting in their living room, Priscilla Bach suddenly started reflecting on the state of the Milky Way research. Bart, get out of spiral structure. The future is in star formation. And he actually followed her advice. Because, the thing is, although we were running aground in terms of trying to understand the maps of spiral structure of the Milky Way, all this information about the gas and the connection of the gas clouds to the stars that form out of them was just accumulating. It was just an amazing collection of data. And everyone began to realize, well, we may not know what spiral structure is, but we can certainly look at the regions where gas clouds collect and form stars. And so people started over in the 70s with a new tracer rather than using H1, the neutral hydrogen gas. It turns out you can, when gas gets very dense, it forms molecules like carbon monoxide. And so that carbon monoxide should be more clumped, more spatially located in clumps. And so people started the whole process over trying to map out the distribution of CO in the same way that they mapped out the H1. By this point, of course, there were people that were skeptics, and there were people that thought, well, maybe this will be the time. This will be the time it works. I don't really have time to go into it because I have some more things I want to share. But what I do want to say is that it ended up being inconclusive. The data of the 70s into the early 80s said, well, okay, we may see some more structure. We may see hints of spiral arms, and you can certainly sit down with someone and make an argument that the structure you see in the data is a spiral arm. But a skeptic can poke a lot of holes in your argument, okay? And of course, scientists are skeptical. And so it was very hard to get us to converge to any kind of map. And so what happened was that lacking a good map, eventually people sort of gave up. And when people needed a map, they just had to pick one. And so here's a whole set of different models that people had proposed sort of over the 80s, 90s, and 2000s. And eventually we'd all sort of seemed to settle sociologically for who knows what reason on this one. And this became our sort of model of spiral structure. Now I want to back up one step and show you, these are all these different models of spiral structure, all the different purple lines of how the spiral arms might be aligned in our galaxy. The one thing you may notice about them is one thing they have in common is they all are sort of empty in the center, right? And that was a huge clue as to something going weird in the center of our galaxy. Now, it had been speculated for lots of time that there was that the Milky Way might have a bar, that is, that the stars, rather than being sort of organized in just a disk, have an elongation. But it wasn't until the 90s into the 2000s that we really had infrared astronomy allowed us to see through all that dust, to see all the stars glowing in the center of the galaxy. And it became very clear when you looked at the stars in the center of the galaxy that there was a big concentration of stars, and it was asymmetric. It was arranged in a bar kind of shape. And so it's a little hard to see in this image, but if you really squint, you can imagine the left side is a little taller than the right side. So essentially, if over here it's a little taller and it gets narrower, that's because the bar is receding into the distance as the right side. And so the 90s and the early 2000s became the age of the bar. Forget about spiral structure. We're sort of stuck there, but let's work on the bar. And so we sort of filled in that center of the galaxy with a bar. But then the question is, how does it relate to what happens further out? Well, that's where I started my career. So essentially, spiral structure was sort of at a dead end. The bar was starting in place. So using data from the Spitzer Space Telescope, I accidentally discovered that the bar seemed to be much longer than people had thought, about 30% longer. But that was important to me anyway, because it meant that making the bar longer brought the bar out to the point where we seemed to think that the spiral structure started. And so it sort of connected the bar region out to the spiral region. And so I became interested in spiral structure and have sort of been stuck in this for a long time. So I'm going to skip through this diagram because I don't have time to explain it, and I want to get to the next thing. So where were we? In 2008, as part of the GLIMP survey, and those of you, probably people have seen these posters here, right? This is part of an infrared survey of the plane of the galaxy where we can see all the star formation, we can see the stars. We decided to have a meeting at the American Astronomical Society meeting in 2008 where we got together astronomers and said, let's talk about spiral structure again. And one of the fascinating things about this, and the other thing I said in this meeting, and I'm thinking what a fool I was at the time for even thinking to do this, it says, let's actually get all the people together, collect what information people have, and try to come up with a new visualization of the Milky Way, a new sort of artist picture that includes the bar properly and includes the best spiral arms we can put in. And so that was the origin of this image that's shown on the right. Some of you may have seen it. It's in a lot of places now. If you Google Milky Way, you'll find it. But what was interesting about this picture is you can sort of think of this picture as a model. It's sort of our best guess, and you can test it, right? And you can see, okay, well, if this is the way the Milky Way looks, are those things there? Now, this is a piece of art. The sun is on the left. It's an art that we tried to make sort of reflect the data. So here's the sun. Galactic center is about 27,000 light years distant right over here. You've got the bar. That's this collection of old stars in this sort of diagonal configuration. You've got arms coming off the bar, and then you've got other arms in between. And in the process of making this image in 2008, an astronomer who was invited to give a talk at this meeting discovered that this structure here, which sort of seems to wrap around the bar, it's not technically an arm, it's more sort of a ring sort of structure. This was called the near 3 kiloparsec arm. It was found during that golden age in the 50s, 1957, but Tom Dame found that there was a far side counterpart in 2008, which was a really amazing thing. I mean, here it was, this thing on the near side turned out to have something on the just on the other side of the bar that was identical in terms of its physical properties, but had been missing for 50 years. And so it sort of it made the galaxy somewhat nicely symmetric. And so that went down about 2 months before we were going to make this artist picture. It led to a lot of revisions at the last second. And then in 2011, 3 years after the artist picture came out, the artists actually got contacted by Tom Dame, the same astronomer, who says, "What did you guys do to place this arm way out from the sun, beyond the center of the galaxy? How did you guys decide to put this arm here?" And he said, "Well, we just took this stuff on the near side and flipped it over because we didn't have any information about the far side of the galaxy." He says, "Well, the reason I'm asking is because I'm finding that there actually is an arm there, almost exactly where the artist put it, and it trails off almost exactly where the artist has it trails off." And says, "Do you have access to some data I didn't know about? Did you analyze this to?" It's like, no, we just flipped the near side over. But yeah, so this artist picture was sort of interesting because that made me feel good about this picture. I mean, I felt sort of queasy about it because it's like, well, I know all the skeletons in this thing, but like, wow, it actually predicted something. And so when Tom discovered the two arms, and I made a pilgrimage to Harvard to basically sit at his knee and learn from him, and then and we continued to sort of test this model, and it's like it seemed okay. And I said, well, maybe this is the way this works, until 2018. Now in 2018. By this point, the Gaia satellite had been up for a while. It had been collecting the parallaxes to billions of stars. So we had super precise positions of stars. We also had measurements of the amount of dust towards each star, the so-called extinction. And so with all of that information, you can actually sort of invert the information and make an estimate of where the dust is. It's like if you have enough stars with enough measurements of their dust towards each star, you can make a picture of where are the dust clouds. And so I was at a meeting in 2018 where Greg Green showed the following picture. Again, this is a picture showing Galactic Center to the right. Then the sun would be at the center and it would be going this way. And you can see there's a band of dust here. There's a band of dust here. Maybe there's a strange band there. Some little clumps here. But it doesn't look like this beautiful picture that I was just showing you, okay? And then Greg Green showed that in the morning, and in the afternoon, a French astronomer, Rosine Lallemant, using parallaxes, but a completely different analysis technique and a different sort of set of data, which is why Greg's has a chunk taken out, but a different set of stellar data to measure the extinction. Rosine gave her map, and they look pretty similar. That you can see those bands that are on, both inside and outside the sun's orbit. You can see the stuff that's a little closer in. And it doesn't look like spiral structure. And Greg Green at that meeting, he doesn't remember saying this, but he says, it sounds like me. He said, he turned to me during this presentation and says, I don't see a spiral structure. Do you, Bob? and I said, well, I don't know. And at first I didn't know what to think. And I didn't know but I was seeing two different groups coming up with the identical maps. It's like, well, what do you do with that? Well, what's happened since then, over the 2018 to recently, is that all of the maps are now lining up with each other. Every time people try to map out the structure of dust, of gas, they get the same map. And so it doesn't really matter how to interpret it. It is what it is, right? And you can say, maybe I don't know what I'm seeing here, but what I am seeing, I can believe. And this is actually a labeled. For those of you who are amateur astronomers and like pictures of star-forming regions like Orion or the Lagoon Nebula or the Eagle Nebula, they're all here, okay? And in particular, let me just point out, in this structure here, there's a little diagonal structure of dust here. There is the Eagle Nebula, there's the Omega Nebula, there's Lagoon Nebula, there's the Trifid Nebula. There's 4 sort of beautiful star formation regions, and they sort of line up in a row in that structure right there. Over here, you've got the Aquila Rift in the Scosen region. Over here, you've got Perseus Cloud and Taurus Cloud, the California Cloud, the North American Nebula, the Cygnus X complex. They all seem to lie in a sort of a line. And so we're really seeing, and this picture is not completely dissimilar from what Bill Morgan said. I mean, he said he saw a band just outside the sun. He saw some stuff inside the sun. But we're getting things in such incredibly crisp resolution and detail that it's hard to believe it's true. I mean, actually, I want to say, now that I am a big convert to these dust maps, I can say that, well, by the way, I should check on how much time we have. It's like, when were we going to end?
A little after 8:30.
A little after 8:30, okay. When these dust maps started to come out, and I couldn't quite understand them, and I didn't quite trust them, I didn't know what to do, and I sort of sat there thinking, what do I do? Meanwhile, a lot of my colleagues at Harvard and Vienna were off and running, and they were interpreting these dust maps. And I sat down and was like, well, you got to be careful. We need to test this. We need to test that. And Alyssa Goodman, who's a professor at Harvard, was like, Bob, why are you being so skeptical? And I said, and I didn't even think before I answered. It's because I'm afraid of having my heart broken. If you know anything about the galactic astronomy, you know that it's been disaster and bash streams and dash streams after one after another. And so I just couldn't believe this moment had arrived, that you could actually have these high fidelity, trustworthy, reproducible maps. And maybe you couldn't interpret what you were seeing, but you knew what you were seeing was true. But you know that in addition to the dust clouds, which are shown in gray here, the yellow point, or the color points, indicate locations of masers where we also have parallaxes. This is independent of Gaia. But they also lie in the regions where you have dust clouds, which is what you would expect for masers, which occur in these very dense star-forming regions. But those color points, I want to emphasize, they seem to agree with where the dust clouds are. But the fits to those things, those lines, are these log spiral fits. Those are not very good representations of that data. In other words, if you try to just say, oh, we have these beautiful spiral arms that are nice arcs passing through the galaxy, they do not seem to fit that data very well. And so the beautiful picture that was sort of the beautiful model that was underlying the artist picture that I showed you earlier is starting to fall apart. And we have to replace it, and we're not there yet. But I'll tell you some pieces that are coming along. So now there's other tracers, and basically the bottom line is everything you can plot that traces where dust and gas stars should be forming is all agreeing. There's different ways of doing it, and it all sort of fits together. So when the models fall apart, and that's what's happening to me, you have to go back to the data and figure out how do you restart? How do you put things together? And And so that is where we're going to, another story. So I showed you that place, that little section of the galaxy with the Eagle Nebula or Omega Nebula. You may have noticed that it was sort of angled inward very steeply towards the center of the galaxy. It was traditionally called part of the Sagittarius arm, but it appears to be what we would think of more as a spur. And so let me show. And this is done with these collaborators. Mike Kuhn was the first person who came to me with the data. Catherine Zucker, you'll hear more about. But this is a whole team of people, particularly people who are good on statistics, which is very helpful when you're trying to deal with large data sets. And so we actually put together an analysis of this. This shows the glimpse data, and each of the points that we mapped, we're showing where is it on the sky. So each of these circles is indicating the distance to things. And so the S50, Sharpless 54, the Eagle Nebula, the Omega Nebula, all these things we can map out and see what their structure is. And when we make the face-on map, we get something that looks like the following. Here is the distribution of these things in space, okay? Here is what we sort of expected from the model. Now, by the way, I do a lot of talks now at a planetarium in Waukesha, and I say to sixth graders, do you remember when in science, you have your data and your model, and so do you think those points line up with that gray band? No, and so obviously we need to fix the model, right? And we don't know how we're going to fix the model, but we're there, and we're working on it. So that's where that's going. But now sorry, I've overstuffed this talk. I apologize. But now I'm going to switch gears a little bit and talk about the hard right turn that I mentioned. Because we have these maps of the dust clouds, we can not just see where the dust clouds are, but we can also see where the voids are. And it had been known for decades, and this is actually a lot of this work was done here in Wisconsin, that the sun exists in something called the local bubble. That is, there's a sort of region of interstellar space about 600 light years across, where there's really pretty empty, and we're sort of in the middle of that. Don Cox, who I came to Wisconsin to work with, he hired me, and Ron Reynolds, who just recently passed away. Both Don and Ron have passed away in the last few years. But they really led this change in focus among astronomers from thinking about spiral arms to thinking about just the bubbly ISM, the idea that the galaxy could be filled with explosions and that heats up gas, and you get these bubbles and networks of bubbles and Swiss cheese. And this whole picture that they developed almost from pure thought, really, back in the 70s is turning out to be totally true. And this is where I'm going to break into Catherine's talk, because Catherine, who's now a research scientist at Harvard, but she let me use this. And what you'll discover is that younger people have much better graphics. And so what Catherine did is she took those dust maps, those maps of the dust clouds just around the sun, and she realized that, if you look at where the bubble is, the bubble surrounding the sun, all of those dust clouds are sort of right on the boundaries. And so she basically realized, all the young nearby stars are sort of surrounding on the boundary of this bubble. And so some of these, if those of you who've taken images of the night sky, you might know about the Ophiuchus region, the Pipe Nebula, chameleon clouds, the Taurus clouds, all of these things which are sort of all over the sky because they're surrounding us in all directions, actually all trace the boundary of a bubble. And so Catherine actually, there's a little picture of Ophiuchus region. There's a single star-forming disk or planet-forming disk in Taurus, HL Tau. But this whole thing is basically wedged in around the sun, if we zoom into sort of that picture, and see what I mean about the graphics. And so we can go ahead and look with this picture, this amazingly crisp cartography, we can look at how this bubble might have been formed. With an explosion, 14 million years ago, exploding and starting to form the local bubble. I didn't let it run all the way. So we'll let it grow. That's the local bubble. And it's going to continue to expand. So this is the time 10 million years ago and 9 million years ago. This is, of course, a simulation, but it's sort of saying this bubble expanded, compressed some of the gas around us at the edge of the bubble, and that was what triggered the stars to form around the sun. And so, so that's sort of a cartoon, but there's actually based on real data, which is shown on the right. So there's a little simulation where you're actually just mapping out the motions of things in data. This is not what we were expecting. Actually, I'm going to skip through that. But Catherine shared this nice little video. This is actually the Zoom call where they discovered this, where they actually could say, oh my gosh, what is this? So they were looking at the structure of all these things around the sun. And you can see what they're rotating here is a 3D cube of dust out to a distance of about 3,000 light years from the sun, where they're trying to identify the structures, where the stars are forming, the boundaries, the bubbles. There is a never-ending list of things that we can do with this data now. It's pretty amazing. So again, if we look, the zoom in from the location of the center of the galaxy, so here we are, we can map out this bubble, and it's just pretty amazing stuff. Now, I actually, when this came out, and Catherine shared the paper with me, I contacted Ron Reynolds. I sat down and showed him as he was amazed, and I said, you've got to talk to Don. Don was down in Florida. Don, at this point, was starting to develop signs of Alzheimer's, and so Ron talked to him, and Don said, well, I don't really remember this very well, but I told Ron to say, the message of this paper is, Don Cox was right all along. And Don said, well, I like the sound of that. And so essentially, you know, we now can visualize and model and understand this local bubble around the sun with just incredible precision and times and, you know, movies in 3D, and you can do it all in 3D, which is, again, challenging me as an old guy, but so fun to get involved with. But the story doesn't even end there, because another student, I think one of the things is if you don't tell students, if you don't tell them something's impossible, they'll just go ahead and do it. And so what I'm, oops, crap. Let me go back and find that slide. So the next chapter in this story is done by a student, a grad student in Vienna, but who actually was an undergraduate here at UW-Madison named Cameron Swigum. Because in addition to looking at where the dust is and where the clouds are, you can actually find groupings of stars in the sky called clusters. And you can measure their positions precisely. You can measure their velocities precisely. And you can that means you can calculate their orbits going backwards in time. And that's what this is going to show. You see a collection of clusters all around the sun at the current time. And now if we run them backwards in time, assuming something about how the gravity of the galaxy works, we find that if you look at all the young clusters around the sun, the majority of them originated in 3 spots. So in other words, what we can say is 30 to 40 million years ago, which by the way is since the dinosaurs went extinct, right? So this has all been happening since the dinosaurs. 30 to 40 million years around, in this neighborhood of the sun, in the region that the sun inhabits, the solar neighborhood, there was 3 large giant star formation regions, each one of about 1 million solar masses of material. And out of those regions, dozens of clusters formed. And then as time went on, they dispersed across the galaxy and dispersed across our sky. But we now have the ability to run that backwards. So I sort of say this is like sort of having the ability to unscramble an omelet and discover you started with 3 eggs, right? And the 3 eggs, the things that are making up the distribution of all the young stars around our solar system, was these 3 star formation regions that Cameron Swigum has identified with sets of clusters. So for those of you who don't know what I mean by clusters, here's some pictures of some of the clusters. There's about a total of 200 of them that make up these 3 families. And so there's the Alpha Per cluster, the Trumpler 10, Messier 6, that probably is, maybe some of you know that one. But all these clusters, essentially we've discovered that they came from 3 sort of origins, okay? And then have sort of mixed together over the last 30 to 40 million years in our solar neighborhood. But the story doesn't quite stop there. So you know, again, the thing that's fascinating about this is what Cameron also went on to show is he showed if you follow where those clusters have moved over the past 34 million years, each one of those clusters had a lot of massive stars, many of which have exploded. And each explosion carves out the interstellar medium. And so a lot of those bubbles that we're seeing in the dust maps are the locations where the clusters have actually carved out the interstellar medium from explosions. I didn't think this was possible. When we looked at the distribution of the interstellar clouds and the dust it's like, well, that's nice. We know where it is now, but we'll never know where it came from. And Cameron, like within a year, proved me wrong, okay? Because he said, no, we know where they came from because we know where all the young clusters were, and when they formed, okay? So we're putting together this amazingly detailed picture of how everything has gone down in the neighborhood of the sun over the last 30 to 40 million years. So I'm going to leave you with one last thought. This is the part that's not published. Where did those clusters, why? Why in the solar neighborhood 30 to 40 million years ago did you have three major groupings of stars all forming at once, or all starting to form at once? And so it sort of gets to the question of, the picture on the right shows those dust maps, and shows where the clusters are now, okay? The picture on the left shows where the clusters were then, 45 million years ago. What we don't know is where all the gas was then, right? But we can sort of have a good idea that there was a lot of gas in these three regions, okay? Because that's what ignited all the stars to form, okay? And so, so why? Why would you get all of those stars forming all at once 30 to 40 million years in the galaxy? Anyone want to guess? Other bubbles? That's a possibility. I mean, except that to get three of them all at once from a single bigger bubble is hard. I think the answer is, yeah?
Gravitational interaction with another incoming galaxy.
That's another possibility. I mean, people have speculated that you could have a cloud fall into the galaxy and it would hit the galaxy and push a lot of the gas into forming stars. But this goes back to the thing I was mentioning at the beginning. Remember that if we have spiral arms in the galaxy, then occasionally a region of the galaxy will pass through a spiral arm. By the way, it's important to realize that the spiral pattern moves at a different speed than the material. So basically, if you imagine riding around the galaxy in circular orbits, you might be going around at a certain speed, but the motion of the arm itself will go at a different speed. And typically that speed is a little slower. So spiral arms are like traffic jams. You go into the traffic jam, you slow down for a while, and then you pick up speed and go out. So your car has a certain speed, but the traffic jam itself, if you were watching from above, could be moving at a different speed down the road, right? The location of the traffic jam. And so it turns out that this is probably due to the so-called Carina arm, which is one of the arms that I mentioned but didn't highlight earlier in this talk. The Carina arm, of all the spiral arms in the galaxy, I think the Carina arm has the best structure, the most reliable structure, the most believable structure. I'm not going to have time to convince you of it, but it's essentially a spiral arm that we know and love, and you can actually see parts of it here in H alpha. That's the Sagittarius part, and this over here is the Carina part, the Carina Nebula, glowing in H alpha. And so this arm, which I can't. It turns out this arm is long, basically tens of thousands of light years long. It's tall, it's very tall, it's very bright, and if we know anything about how things are moving through the galaxy, it seems very plausible that this region of the galaxy that we live in right now passed through that arm about 30 to 45 million years ago, initiating the processes that we're seeing playing out to the current day. So essentially, it's a merging of the sort of two pictures, the spiral arm dominated picture and the bubble dominated picture. And so let me actually skip out of that. So I've taken you a very long way. So from the beginning of the galaxy to the idea that the spiral structure that we knew is falling apart, to now the idea that, well, we still see some spiral structure that we believe, and it seems to be related to the star formation we can basically do forensics on in the sun. And it turns out, strangely enough, I'm not the first person to suggest this. Actually, this is my theory in galactic astronomy. Whenever you have an idea, I did it again. Whenever you have an idea on how things work in the galaxy, you are guaranteed to find that other people have thought of it before. So I will not be the first person to suggest that the structure we see around the sun was created by the passage of the solar neighborhood through the Carina arm. This was first suggested in 1969, and a whole bunch of authors subsequently have suggested it too. The major difference that between their suggestions of this in the past and my work on it now is I have high precision data, right? And billions of stars and giant clusters and 3D maps of the dust. And so as I look at the structure of the Carina arm now, I'm actually able to see the past, the solar neighborhood's past. So to look at the Carina arm that we see in the sky now is to see what the solar neighborhood used to look like 30 to 40 million years ago. And this is sort of a work in progress. So I'm going to end with one last thing, just as a fun thing. So I'm mapping the Carina arm. That's one of the things. The last thing I want to say, and this is really not relating to the talk earlier, but I want to say that I mentioned Nancy Grace Roman and my original entry into this thing, which is to be involved with that galactic plane survey that's shown on the wall over there. It turns out that we are going to have the opportunity to map the galaxy at Hubble Space Telescope resolutions, but the entire galactic plane, right? So I mean, think of every beautiful Hubble picture you've seen of a star-forming region. Now we're going to get Hubble pictures of all of them, okay? And that will the launch of the Roman Space Telescope will be in 2007. And so I was part of a group that made the argument that this is one of the first priorities of the Roman Space Telescope. And I am now the chair, or one of the co-chairs of the committee to design this survey from my mother's basement apartment. So basically, the story is going to continue. Invite me in another 5 years. And so I just want to say that, again, the thing I want to leave you with is just this picture here. This picture is a picture in the infrared of M83. And you can see this beautiful galaxy on the right as seen by Spitzer. But from our point of view, remember, we live in a small section of it, right? We live in a small section of a galaxy. We have an access only to the small part, and then beyond a certain distance, it gets very fuzzy and very difficult. So, I just want to show you, what would it look like if you lived in different parts of M83? Remember the dust maps I showed you, and just think about what would happen if I lived in these different locations at the center of this picture on the left. You would have a very different view of how the galaxy looks. So it's important not to overgeneralize what we see around the sun, because there's a lot of different possibilities, even if you were in the same galaxy. So it's important to not overgeneralize, but it's still the impression I want to leave you with here is it's a lot of fun. Okay, and I literally never dreamed I would be evolving clusters backwards in time, or doing things in 3D, or mapping the entire galactic plane with Hubble Space Telescope resolution. But all of these things have become possible in astronomy now, and it's just going to yield puzzles for generations to come. So thanks a lot.
So if anybody has a question for Bob, wave me down and I'll come to you with the microphone.
Bob, when you're talking about our local bubble, have we found other bubbles that are similar to ours that we can observe from the outside?
Yeah, so we started with local bubble, and actually there's, if you look in the sky, you can see that there are these sort of ionized gas regions, and so you can see what's beyond the local bubble, the next bubble. So in all directions, except for up and out, except for vertically, but in all directions around us, our bubble is joined by another bubble. And then beyond that bubble, there is another bubble, and then sometimes you have these strands of dust. So it's a very complex topology of bubbles and strands and shells, yeah. But you can see that in the 3D maps, so it's like, it is what it is. By the way, I can name a few of the bubbles, like there's the Orion Eridanus bubble and then the Gum Nebula bubble and so on.
Just 3 quick questions. Did you read Bach's book, The Distribution of Stars in Space?
I did.
Okay, is there still good science in there? Is it all deprecated by now?
This is the wonderful thing about galactic astronomy, is that they were looking at the same sky in 1937 as we do now. And so frequently what I would find when I read these old things, because I like to read the old things, I mean, it sort of connects me to the history of it, is that what they're saying is never wrong, but what they're working with a very, very incomplete picture. And so I would say, if you want to know how the galaxy looks, you wouldn't start with a 1937 volume. But what Bach said back then with the data he had then is still a completely valid and reasonable approach to the data.
Sure. And then,
But they just lacked the giant data sets we have today.
sure. And then my last question was, one of your slides had a list of discoveries in the 1950s.
Yeah.
And one of them was Norma Scutum Arm
Yeah.
by Thackeray.
Yeah.
And then the other author was Optical ABSN. And I was just wondering what that was.
Oh yeah. So that's actually one of my favorite spiral arm discoveries. Most spiral arm discoveries were based on finding gas at you would see it coherently as a function along the galactic plane at different velocities. The Norma arm was an exception. Thackeray, who was a British astronomer, he looked at two B stars just to the left of galactic center, and another pair of B stars. B stars are just sort of hot, massive stars. OBAF, if you know the spectral classification. He looked at a couple of B stars to the right of galactic center, and he saw absorption lines in the two stars to the left at a velocity of plus 80, and he also saw absorption lines at the two stars on the right at a velocity of minus 80. And he just said, oh, I must see a spiral arm on the basis of absorption lines in 4 stars. That was the level of evidence, at the time. I mean, it's crazy to imagine claiming an entire spiral arm off the basis of 4 absorption lines. But that was the claim, and that stuck, and that propagated through. And the data, that very, very fragmentary data that he had back then actually continued to be borne out by subsequent evidence. So it's like right at the edge of anything you might believe. Actually, in my case, beyond the edge of what I would believe.
With all of the enormous amount of data that you now have, has there any thought of creating an AI to deeply analyze it, do things that we can't do ourselves?
Yes and no. I mean, one of the challenges is what we have in this 3D dust maps, for instance, is what we call a very complex 3D volumetric data set. Essentially, you've got the density as a function of position over this cube, and identifying structure in it is a challenge. I mean, you can you can look at it and say, I see that, and I see that, and I see that, and label them. I mean, we do that in astronomy, but it becomes very subjective and difficult to reproduce, and so people are trying to develop more unbiased methods that sort of say, how will I define the structures I'm seeing in this thing, and pull it out as an aggregate list as opposed to just here you are. And so, but in terms of AI, in terms of interpreting what you're seeing, you use the computer to identify structures in a systematic way, but to identify what those structures are takes experience and thought and usually other data sets that you have to bring in to bear. So it's not the kind of thing that's amenable to, I think, an AI. I guess really the fundamental problem with using an AI to try to create is there's no comparable training set. AI is good at finding structures that you train it to find and working with patterns that you train it to do. But we're sort of this is the first data set of its kind. So you have to sort of work on it as it is, if that makes any sense. So.
Was there a question up here somewhere? Jürgen?
Well, I'll answer one. An area of mathematics that's being used to things is something called persistent homology. And I actually took so it comes from the algebraic topology. I took topology in college, and I gave away my topology book thinking I was retiring. Well, because I am retiring, and now I need it back. Because I need to understand topology again that I had studied back when I was a student in school. So, yeah.
Well, I hope that topology hasn't changed as much as this has changed over the years. Curiosity question, how has the diameter of the Milky Way varied over the years? Has it been about the same for the last 80 years, or?
You mean our estimate of the diameter, or the diameter?
Yeah. Yes.
Yeah, no, actually, it used to be that one of the fundamental things we tried to understand our galaxy is what's the distance from us to the galactic center? Like what's our galactocentric radius? And then that gives you a sense of the scale. It used to be that it was fluctuating by factors of 20, 30%. We're down now to about 3%. So in other words, we think 2 or 3%. We actually know the distance to the center of the galaxy to within 2 to 3%, maybe even better. The total diameter depends on where you draw the outer boundary, and that's going to be a subjective thing. You have to decide what marks the outer boundary. Unlike that terrible Star Trek episode, there is no energy barrier at the edge of the galaxy that we can use as the outside. So it becomes a subjective process. Yeah.
Will Gaia help us actually find what we will end up defining as the edge of the galaxy?
Well, what I can tell you about that is that Gaia has enabled the study of the motions and positions of stars very, very far out towards the edge of the galaxy. But the galaxy doesn't really have a well-defined edge because the disk of the galaxy sort of becomes swamped by this outer spherical thing we call the halo or of the galaxy. And so you have intermixed components that make it hard to sort of define a single structure that you would use to mark the edge. Now, I appreciate the effort. I mean, I've worried about this, but it's a slippery thing to define. But more data never hurts. So.
What's a galactic year? And more generally, is the galaxy getting smaller? Is it getting bigger? Is it speeding up? Is it slowing down?
A galactic year depends on how far out you are, just like it does for the solar system,
Sure,
right? I mean,
of
our
course.
year is a year, and then
But
Mars
for
is
the sun, do we know that?
From the sun's position, the galactic year is 236 million years. So we go once around every 236 million years. Which, by the way, if you remember, the unscrambling stars that we're seeing, that's about 40 million years. So it's not even a quarter of an orbit. And so we sort of feel fairly confident in our ability to calculate the motions of these things backward in time, just a quarter of an orbit. A full orbit or more would be a much more complex or difficult process.
So if we just wait for another quarter orbit, we'll have a much clearer picture of that.
Well, actually, that works. There's two other things. We get further along, but the other thing about the sun is it oscillates above and below the galaxy. We have some vertical motion, and we just happen to be right now, right in the middle of the plane of the galaxy. Give us another few 10 or 15 million years, and we would be high enough above the galaxy. I mean, just barely, but it would be enough to get a little bit of a top-down perspective, and all these questions would not be a problem. Okay, so yeah.
We're between north and south node of the galaxy.
Yeah, we're in the worst place in terms of having the dust block our way. So.
I'll take the last question then. You showed the diagram briefly that you created in, I think, 2008, the very famous, portrait of our galaxy, and you very strongly said that things have happened since 2008. You now disagree with the appearance. Do you have a new diagram, or what you're saying is you just backed off of that certainty?
I look at the picture now, and I know what needs to be fixed. I know what was wrong and why it was wrong, and I know what needs to be fixed. I also know I'm also much more knowledgeable what I didn't know. Like what would I erase? Nope, sorry, don't fill that in. I have actually talked with the Gaia team. It's like, you guys need to make a new visualization of the Milky Way, and I've been pushing. It's like, because I think they deserve the right to do that. So we actually organized a meeting in Leiden last year to try to talk about it. But it's a very, very hard process because you have to know everything about the galaxy. I was foolish to make that 2008 image. I was relying on these models, and now that we're sort of more of a data-driven thing, it becomes a very daunting task. But it has to be done. And so I'm in discussion with several groups that all have interest in it, but also have trepidation about doing it. But it's amazing that it hasn't been replaced with any significantly improved version since 2008, and it needs to be. So stay tuned.
Bob, thank you again very much, and I promise we won't wait 40 million years before we have Bob back for an update.
Well, Bob, I have to speak for everyone, and I think this has been way better than watching an episode of Nova. It's been a privilege and a very fascinating and very gripping presentation tonight. So On behalf of the society, I would like to present you with, I guess this is a replacement mug. Last one. So on the behalf of the society, I would like to present you with our official MAS logo embossed coffee mug, or whatever else type of mug you want to use it for. So, so it's great to see you again, and we hope to get another one of your presentations before too much time passes.
I'll send when there are press releases about these kinds of things, I'll send them your way so you know what to be watching out for, because there are going to be many more, I think, in the next few years. So.
Great news. Well, all right. Just before we go tonight, I would just like to say that we will be back here again on Friday, August 9th. And we are going to have Justin Vanderbook from UW-Madison, the physics department, give a talk entitled Astronomy with the Highest Energy Light in the Universe. And I guess that means gamma rays. So come back and see us on Friday, August 9th right here, and you'll be able to enjoy that presentation. So that